Good morning, everyone. It is my pleasure to present our paper in FCS 2011. My name is Jung-Hyun Kim, and I am now studying at Seoul National University, South Korea. The title of our paper is An Efficient Software Shared Virtual Memory for the Single-Chip Cloud Computer. This is a joint work with Sang-Min Seo and my PhD thesis advisor, Jae-jin Lee. In medical systems, on-chip interconnect becomes a major performance and power bottleneck. It consumes a significant amount of the power budget. In addition to this, hardware-based HTTP protocols generate lots of messages. This worsens the situation. So many studies have been done on on-chip interconnect, but they increase chip design complexity and the high hardware evaluation cost. So we think software shared virtual memory can be an alternative of the hardware cache cross mechanism. So this is the single-chip cloud computer. Recently, Intel announced an experimental medical processor called single-chip cloud computer. It consists of 48 cores. It is basically a memory caching architecture, so there is no hardware cache cross protocol at all. The below diagram shows the overall architecture of the SSD. It has 24 tiles in a 6x4 array. Each tile, it has 2 Pentium P54C cores with 16 kilobyte L1 instruction and data caches. Each core is supported by a 256 kilobyte L2 cache, but there is no cache cross protocol. In addition to this, there is a 16 kilobyte messaging caching buffer for communication between cores. And 4 DDR3 memory controllers are attached like this. And let's think about how to run a multi-threaded program on the system. What is I'll continue. How to run a multi-threaded program on the CC? We cannot run it directly on the CC because there is no hardware cache cross protocol. So we can think two possible solutions. First one is routing the program using MPI, messaging caching interface. But it is hard to program and it requires lots of effort. So we can think second solution, running it on the software's VM. In this case, the program does not need to be modified. So in this paper, we propose an efficient software shared virtual memory for the single-chip cloud computer and reports some preliminary results. Software SVMs were originally developed for distributed memory multiprocessors to provide an illusion of a single shared address space. Previous software SVMs guarantee memory consistency and coherence at page level. They are based on the page fault handling mechanism. In order to avoid page ping-ponging, they support multiplier protocols by managing twins and dips of shared pages. So our software SVM is based on the CRF memory model and provides less consistency. Thanks to the CRF memory model, it does not need to manage twin and dip pages. We could avoid a complicated protocol between cores because the main memory can be configured to be physically shared between different cores. Our software SVM is based on the CRF memory model. I will briefly introduce the CRF memory model. In this model, all memory operations are performed locally in semantic caches called sessions. CRF stands for commit, reconcile, and advance. As its name indicates, it consists of 3 operations. A commit operation updates data in a sesh to the main memory. Normal store operation just updates to the local cache, not to the main memory. So we need to update to the global data. We need a commit operation. A reconcile operation purges clean data in a cache. In order to read the last updated value, we need reconcile the cache first. And the advanced operation enforces memory access order. We implemented a release consistency on the CRF memory model. Let's see how our code translation works. We assume the three arrays A and B, and C are shared. The red circles indicate load operation. As I said before, we need reconcile operation before the load instruction. So we insert reconcile operation before that. The blue circles indicate store operations. As I said before, we need commit operation after the store. So we insert commit operation after that. So we inserted the reconcile commit operations, and this slide shows how our software's VM works. First, these two reconcile operations purge AI and BI from the stash. And then AI, BI are loaded. Since they are not in the stash, we need the data from the main memory to the stash. So with AI and BI from the main memory to the stash. And then the core can read AI and BI from the stash. The values are added and the result is written back to AI. This store operation is just performed in the local stash. And then, since the AI is now in the stash, core can just read AI from the stash. The last commit operation updates the main memory, updates the AI to the main memory. So after this, other cores can read the updated AI. However, it incurs too much overhead because every iteration in the for loop, we need commit and reconcile operations. So we need some optimization like moving them out of the for loop. Let's see how our optimization works. First, let's concentrate the reconcile operation first. When you move out the operations out of the for loop, we need to merge all iteration or invocations of each iteration to a single summarized operation. They have four arguments. First one is start address. Second one is the number of items. Third one is stride. The last one is size of an item. So when you merge the data, the parameters are changed like that. And then we move reconcile operation there. And then think about the last reconcile operation. We want to move this operation to that point. However, this is not possible because it does not guarantee the value of array C is the last updated value. Let's think about the case. For I executes the critical section, and then it updates the values of CI. And then next for J enters critical section. Because there is no reconcile operation, core J can read state data in the local stage. So we have to reconcile operation located to that point. So this is the final optimization code. Two reconcile operations are moved to that point. The last reconcile operation is located after the log. Then let's think about commit operation. We have to commit AI and CI before the log to release consistency. As the same example, the core R executes the critical section, and it reads and updates the values of C, and then it does not commit because it does not commit. In that case, core J cannot read the update value by C. So we need commit operation before log. So this is optimization. So this is our final code. Yeah, we optimize the performance with this optimization. And then I'll talk about our runtime system. Each core runs its own SEC Linux kernel. We modify three modules in the Linux kernel. First, Thread Manager. It dispatches threads onto other Linux kernel.